International harvester mechanics are working round the clock across the country. Tractors are coming straight back from the field. Final drives shattered. Not a handful, hundreds. The company has already spent $20 million, and this was only the beginning. After World War II, the American tractor market quietly became something its founders never intended: an open horsepower arms race. I.H., Ford, John Deere. All three pushed power numbers upward with every model cycle. The problem was never the ambition. The problem was everything beneath the engine. The Farmall 5.6? Oh, is where this story gets expensive. In the final stretch before the 1958 launch, I.H. engineers bumped engine displacement at the last minute. The specific goal was to outgun the John Deere 730 on spec sheets. The engine got bigger. The rear final drive didn't. What they bolted it to was the same drivetrain architecture as the original Farmall M, a design from 1939. Under real field load, the ball bearings and the bull gear pinion seats couldn't hold. They'd migrate out of their housings, seize the gears, and blow the rear axle housing apart, sometimes mid-planting, sometimes mid-harvest. The 4.6 followed the same logic. A bigger engine dropped onto an unmodified rear axle borrowed from the Farmall H. Same shortcut, same result. By June 1959, I.H. recalled every 4.60, 5.60, and 6.60 in the field, failed or not. Dealers replaced final drives for free, round the clock. The bill came to roughly $19 million. In today's money, over $200 million. I.H. caught Deere on horsepower. The cost of catching them consumed 5 years of market position. Ford's version is quieter and harder to defend. The 6000 Commander launched in 1961 with Select O-Speed, a 10-speed hydraulic mechanical transmission that shifted under load without a clutch. The concept was legitimate. The execution wasn't finished. Under 66 horsepower, the unit failed, consistently. Ford's fix wasn't to strengthen the transmission. It was to detune the engine from 66 to 62 horsepower. The 1963 Nebraska tractor test put that number on paper officially. A separate safety recall followed. The transmission could drop into neutral without warning on a slope. Dealers called the change an improvement. Farmers read the test results. John Deere's own 2010, launched that same year, ran a new proprietary engine precise enough to make field repair a specialized job. And most dealers didn't have the tooling. The hydraulic pump leaked at the fittings chronically. Getting it sorted in the field took anywhere from 8 to 20 hours. During harvest, 20 hours isn't a delay. It's the harvest. 3 companies. 3 completely different failure modes. One shared cause. The engine grew. The rest of the machine didn't. After 1959, something shifted in the market. I.H. had burned $20 million and 5 years of goodwill. Ford had published its own failure in a Nebraska test report. The window was open, and a second wave of manufacturers walked straight through it. Allis-Chalmers, Oliver, Massey Ferguson, Case. All 4 moved aggressively into the 100-plus horsepower segment. All 4 believed the gap left by I.H. and Ford was theirs to fill. None of them tested hard enough for what American fields actually demanded. The Allis-Chalmers 190XT had a strange problem. It was better than the factory admitted. Mechanics in the field were pushing PTO output to around 125 horsepower, well above the advertised figure. The engine could handle it. The transmission couldn't. Gears jumped out of 5th to 6th and 7th to 8th under wear. The hydraulic pump's priority valve deteriorated under load, collapsing the lift system at exactly the moment you needed it most. AC knew the real numbers. They never published them. The tractor was quietly sold below its own potential, because putting that potential on paper would have exposed the drivetrain's ceiling. Oliver's entry into this segment tells a different kind of story. The 1250 wasn't built in Ohio. It was a Fiat 415, designed for lighter European soils and smaller European fields, rebadged and shipped to American dealers. Oliver's network didn't carry Fiat-specific parts. They had to be ordered through an importer, adding 4 to 8 weeks to every repair. In a country where planting windows last 3 weeks, that's not a logistics issue. That's a crop decision made for you by a parts catalog. The tractor failed hydraulically and mechanically within the first season. Agricultural consultants stopped recommending it almost immediately. Massey Ferguson arrived at the 100 horsepower segment with the 1805, and the timing was almost deliberately catastrophic. The machine was conceived in 1968 to 69, built around a Perkins Vifoff 8.510 engine that consumed fuel at a rate that made sense when diesel was cheap. It hit the market in 1971. 2 years later, the 1973 oil embargo rewrote the economics of every high-displacement machine in the field overnight. The 1805's power advantage became an operating cost. The hydraulic system leaked under pressure. The cab was poorly designed. Operators reported physical fatigue after 6 to 8 hours. The crisis didn't create these problems. It just made them impossible to ignore. Case's 1070 Agri King ran hot and shifted inconsistently. What made it particularly damaging wasn't the failures themselves. It was the silence around them. Case released no public documentation explaining what was wrong or what had been corrected in subsequent builds. Dealers couldn't tell customers what had changed. Farmers didn't wait to find out. They bought Deere. They bought IH. The 1070 never established Case in the segment it was built to own. 4 brands, 4 different paths into the same outcome. The failures in parts 1 and 2 had a common shape. Engineers kept familiar architecture and pushed it past its limits. The machines in this section made a different bet entirely. They redesigned the architecture itself, and they discovered a problem nobody had fully accounted for. When you build something genuinely new, the entire world around it is still old. International Harvester's 35882+2 is the most instructive example of this. The concept was striking. Take the rear half of the proven IH1086, extend the frame, attach a front axle unit from Kymco, a Komatsu subsidiary, and create an articulated machine that offered 4-wheel drive capability without the cost of a full redesign. On a diagram, it made sense. In a field, the contradictions surfaced fast. The 16-speed turnaround transmission was carried over from the 1086. The same unit that had worked reliably in a conventional machine now sat inside a new articulated geometry, carrying different stress vectors under heavy draft. The hydraulic pressure in the TA circuit became unstable under load. The transmission would hunt between ranges at the worst possible moments. But the sharper problem wasn't mechanical. It was the gap between what the factory approved and what dealers actually sold. The operator's manual stated clearly, front dual wheels not approved for this model. The dealer option catalog listed those same duals as an available fitment. Dealers installed them on request. When the driveline and frame failed under the extra stress, the warranty claim came back stamped, operator misuse. The factory had protected itself in 2 sentences of fine print. The farmer paid for the gap between those 2 sentences. Versatile's 1150 didn't suffer from internal contradiction. It suffered from scale. Versatile built the most powerful articulated tractor on the North American market. A Cummins KTA 855 producing around 470 horsepower. The machine was real. The infrastructure to support it wasn't. On hard prairie soils under full draft, the transmission couldn't absorb what the engine produced. Documented failures described it as the driveline destroying itself under its own output. And when something broke, the dealer network, strong in Canada and parts of the Midwest, sparse everywhere else, simply didn't stock the parts for a machine this large. Repair in the field wasn't difficult. It was essentially impossible. Versatile had built ahead of the market's ability to maintain what it was selling. The Belarus 510, the MTZ 50 and 52 platform, entered this section from a completely different direction. Not a private company chasing horsepower, but a Soviet state manufacturer chasing volume. The tractor was marketed on 2 claims, low purchase price and durability. Neither held fully under scrutiny. The 12-volt electrical system failed systematically below -15 degrees Celsius. Starters and alternators went down across grain region MTS reports every autumn and winter. The hydraulic seals were Soviet-grade nitrile that stiffened and cracked in frost, leaking under pressure in the exact conditions the machine was most needed. The real interval to first major overhaul came in well below the factory's stated figure. The purchase price was genuinely low. The 5-season total cost of ownership, downtime, parts, logistics, documented records from comparative reviews of the period show it exceeded the machine's own purchase price. The cheapest tractor in the class turned out to be one of the most expensive to keep running. 3 machines from 3 completely different systems. One shared failure. They all built the product without building the world the product required to function in. By the late 1990s, the tractor market had consolidated into a short list of large manufacturers: Deere, New Holland, AGCO, Case YH, whose pricing reflected decades of brand equity as much as engineering cost. For a small operation in the American Southeast, or a mid-size farm in Eastern Europe or Latin America, a new John Deere wasn't a purchase decision. It was a financing conversation that sometimes lasted years. That gap was real, and Mahindra read it correctly. The Indian manufacturer had been building tractors since the 1960s under license from International Harvester, and by the early 2000s it was pushing aggressively into the U.S. market through independent dealerships that needed an entry-level product to offer buyers priced out of the green and red options. The 255D Power Plus was that product. On paper, it made sense. 25 horsepower, compact, priced $3,000 to $5,000 below comparable units from Kubota or Case IH in the same class. For a small farm, a hobby operation, or a rural property, the number was genuinely attractive. The problems weren't hidden. They were simply deferred. The 2-cylinder 1,490 cubic centimeter engine had no torque reserve for conditions outside what it was designed for. In India, the 255D worked smallholder fields in shorter daily cycles, typically 4 to 5 hours, on lighter soils with moderate draft loads. American buyers ran it 8 to 10 hours a day on harder ground. The engine overheated not because it was poorly built, but because it was never engineered for that duty cycle. The transmission showed worn synchronizers and fluid leaks by 280 to 400 operating hours, before most buyers had finished their first full season. The injection pump was calibrated for fuel quality standards common in India. Contaminated diesel, which is a routine field reality on any continent, jammed it with a consistency that became a known pattern in owner forums within the first 2 years of U.S. market presence. The parts situation turned inconvenience into crisis. Mahindra's U.S. dealer network was built from independent agricultural equipment retailers who needed a budget line, not from a trained parts-stocked service infrastructure. Critical components had lead times of 4 to 6 weeks from the importer. The U.S. harvest window runs 3 to 5 weeks. The arithmetic was not subtle. What made the 255D a case study rather than just a failed product was the way the numbers worked against the buyers who chose it specifically to save money. The initial price advantage over Kubota was real. After 2 or 3 unplanned repairs inside the first 3 seasons, injection pump, transmission seals, front axle wear, that advantage was gone entirely. Buyers who had stretched their budgets to avoid a more expensive machine found themselves having spent the same amount anyway, with a tractor that had fewer hours and less resale value. A 2012 thread on Tractor Buynet put it plainly: inadequate front axle lubrication, drivetrain vulnerabilities, hydraulic leaks. And the commenter noted that competing brand dealers were using these exact failure patterns as sales talking points. When your product's weaknesses are part of the competitor's pitch deck, the reputation problem is no longer recoverable model by model. It travels to everything that comes after. The 255D didn't fail because it was a bad tractor for the market it was designed for. It failed because it was sold into a market it was never designed for, through a network that couldn't support it, on a value proposition that only held if nothing went wrong. Everything in this video so far broke in ways a mechanic could see: a shattered final drive housing, a transmission jumping out of gear, a leaking hydraulic fitting. You could put your hand on the problem. The machines in this section broke differently, and that difference changed the nature of the failure entirely. In the early 2000s, the major manufacturers moved transmissions, hydraulics, and PTO systems onto electronic control architectures. The logic was sound. Electronic management allowed precision, automation, and diagnostic visibility that purely mechanical systems couldn't match. What it also created was a new category of vulnerability that nobody in a field repair situation was equipped to handle. A $50 sensor could hold a $100,000 machine completely stationary, and without a laptop running proprietary dealer software, the operator had no way to know which $50 sensor it was. The New Holland TM190 illustrates this with uncomfortable precision. The machine ran a range command semi-power shift transmission, mechanically capable, reasonably well regarded when it worked. The failure mode that defined its reputation wasn't mechanical at all. Metal debris from the clutch pack settled on the flywheel speed sensor. The ECU stopped receiving a valid signal. The transmission locked out. Mid-field, mid-shift, mid-season. The sensor itself cost under $150. The labor and diagnostic time to identify it, without the right equipment, could run to several $100s and multiple days. Dealers logged these as transmission repairs. The aggregate data made the system look like it had a broad mechanical problem. It had a $150 electrical problem in the wrong place at the wrong time, inside a diagnostic architecture most operators couldn't access independently. The range command also developed genuine hydraulic instability in the clutch packs, inconsistent pressure producing hard shifts, accelerated disc wear, symptoms that read as mechanical degradation, and masked the underlying pressure management issue. After any clutch or solenoid replacement, the transmission required a factory calibration procedure. Without it, the harsh shifting continued regardless of how clean the repair was. Dealers who didn't run the calibration returned machines to owners that felt broken, because functionally, they still were. The selective control valves failed in the field on relatively new units, 2 or 3 of 4 outlets going dead mid-cycle, error codes in the U5X series appearing without any clear mechanical cause, impossible to differentiate from genuine faults without diagnostic hardware. John Deere's 5055E ran a different set of symptoms toward the same conclusion. The hydraulic pump developed a characteristic chattering, an audible pressure irregularity that appeared consistently between 200 and 400 operating hours, destabilizing both the loader and the rear lift. The PTO clutch failed through a 3-stage chain: hydraulic pressure, solenoid, clutch pack. A mechanic who replaced the wrong node in that chain got the same symptom back 2 weeks later. Multiple owners of the 5055E and its near-identical sibling, the 5065E, reported the same rear lift failure scenario. 6 hours into a field cycle, the hydraulic lift stops responding, the loader keeps working, no clear fault code. Identical behavior across machines, across regions, across seasons. The front axle wore prematurely from insufficient factory lubrication. The CAN bus threw phantom codes on early firmware versions. Warnings that pointed nowhere, resolved nothing, but required dealer visits to clear. Regret buying a 5055E. That phrase appeared in Deere owner forums between 2012 and 2014, with a frequency that was notable specifically because it was Deere, a brand whose buyers are among the most loyal in the industry. When that loyalty produces regret, the machine hasn't just underperformed, it's borrowed against something that takes years to repay. Both tractors failed the same test. In a field, far from a dealer, with a sensor fault and no diagnostic hardware, they were inoperable. Not broken in a way you could fix, broken in a way you had to wait out. Every machine in this video failed because of a decision someone made, a budget cut, a rushed timeline, a misread market, a sensor placed too close to a clutch pack. The John Deere 6930 Premium is different. Its failure point wasn't chosen by an engineer under competitive pressure. It was mandated by a government agency in Brussels. That distinction matters because it means no amount of better engineering, more testing, or longer development cycles could have prevented it. The tractor was required by law to carry the component that would eventually destroy it. Stage 3 emissions regulations, the European equivalent of Tier 3, required exhaust gas recirculation on diesel engines above a certain displacement threshold. The principle is straightforward: route a portion of the exhaust back into the intake, lower combustion temperature, reduce nitrogen oxide output. It worked as an emissions control. What it introduced into a field environment was a heat exchanger, the EGR cooler, running coolant past a component exposed to the full thermal stress of a working diesel engine, bolted into an agricultural machine that vibrated, flexed, and ran for 10 to 12 hours at a stretch. The cooler cracked, not on every unit, not immediately, but consistently enough, across enough hours, that the pattern became recognizable to anyone paying attention. When it cracked, coolant entered the intake, liquid entered the cylinders. The damage from there was internal, progressive, and almost entirely invisible from the outside. Coolant levels dropped slowly, no sudden overheating event, no dramatic warning. Most operators didn't notice the level change until the engine had already absorbed weeks of low-level hydraulic lock stress. By then, the repair wasn't a cooler replacement. It was an engine rebuild. A 2018 Farmers Weekly report described the sequence plainly. The coolant drops gradually, no sharp temperature spike, and most operators only notice the leak after internal damage has already occurred. An Ag Talk comment from 2016 was more direct. Every single machine with EGR valves, coolers, and DPF filters had failed. Not a statistical trend, a personal inventory. The CAN bus connectors on the 6030 series developed oxide deposits that generated false fault codes on the command center display. Error 2000.09 appearing without any underlying fault, requiring dealer visits to diagnose and dismiss. The coolant pump itself failed between 4,000 and 6,000 hours, fast enough in a working machine that it wasn't an end-of-life failure, but a mid-life repair requirement. Without immediate operator response, a coolant pump failure destroyed the engine within 15 minutes at field operating temperature. One documented case at 7,000 hours. A dropped valve seat in cylinder 5. The operator continued working. The engine did not survive. What makes the 6930 Premium genuinely complicated is what happened next. The platform underneath the EGR system was solid, well understood by dealers, respected by operators, with a mechanical foundation that had been refined across multiple generations. Owners who identified the EGR cooler risk early and replaced it preventively, sometimes before any symptoms appeared, reported machines running past 10,000 hours without serious incident. The used equipment market reflected this. 6930 Premiums, with documented EGR replacement history, commanded higher prices than competitors of equivalent age and hours well into the 2020s. The tractor wasn't broken. A component bolted to it by regulatory requirement was broken. That's a category of failure this industry hadn't fully encountered before and hasn't fully resolved since. The 6930 Premium sits at the end of this list, not because it was the worst machine here, but because it introduced a question none of the others asked. What happens when the defect isn't a mistake, but a condition of sale?